Hello everyone, welcome to our channel Code with Sunny, and in this video I am going to talk about the one of the medium type problems of LeetCode, and the problem name is convert sorted list to binary search tree. Index number is 109. Okay, so before proceeding further up to this problem, there is one more variation that comes related to this problem, and the problem is like convert a sorted array to a binary search tree. Okay, so if you have done that problem, then this problem becomes easier to think upon and to work upon this one. Okay, so if you have not done that problem like convert sorted array to a binary search tree, I will recommend to search on the internet and do that problem and then come back to this problem. Okay, so now we're talking about this problem. Let's read out the problem statement first, then we will together find out the best solution of this problem. Given the head of a singly linked list where the elements are sorted in ascending order, so the linked list will contain the elements being sorted in ascending order like -10, -3, 0, 5, and all are in ascending order. Convert this to a height balanced BST. Now you can see there is a term height balanced BST which is actually denoting an AVL tree. If you are not aware of this term height balanced BST, no need to worry about. I am going to explain that also with the help of examples. Okay, for now on, let's move further. A height balanced binary search tree is defined as a binary tree in which the depth of two subtrees of every node. Note that the term every node never differ by more than one. Okay, so this is the basically definition of height balanced BST. Now we will have to find like the okay. So what we have to find? Let us look over that. Convert. We have to basically convert into height balanced BST. Okay. Look over the constraints like number of nodes should vary up to 2 into 10 power 4, and the nodes values lies up to this. So we will think for O of n solution or O of n log n solution. Okay. So let's move further to understand this problem with the help of examples, and we will find out the best solution for this problem. Okay. So let's talk about the height balanced BST first. Like if we have some tree like this one, you can easily see this tree is going to be like height balanced BST. Why this tree is going to be like height balanced BST? Like if you talk about the every node, what is the number of nodes lying in the left subtree and what is the number of nodes lying in the right subtree? Like left minus R, absolute value of this number of nodes in left subtree minus number of nodes in right subtree should not be greater than 1. Yeah, that is, it should be less than equal to 1 for every node. Then it is going to be like balanced binary search tree. Now note that the term binary search tree, you must be aware of this binary search tree. That is for every node's value. Let's say we have this node. Let's say we have this node value as 5. Then the left one should always contain the value less than this 5. Should be 4. And right one should contain the value greater than this parent node. Should be 6. Like that. Or any greater value than 5. Okay, so if you talk about this node, this difference of this one absolute value of L minus R is coming out to be 0. 0 here it is also coming out to be 0, here 0, and here it will coming out to be 1, and here it will coming out to 3 minus 2, 1. You can easily see for every node the difference is coming out to be at most 1. So this is going to be like a height balanced, and this should be a binary search tree. Okay, so this was the concept of the AVL tree. Let's talk about this problem now. Okay, so I've taken one example like this is the linked list, and we need to convert this sorted linked list into a height balanced binary search tree. So one of the way should be like we have this 8 value as one node as the root node, and convert this, and the left one should contain 5 and this one should contain 2, and you can also see I have this one as 9 and this one as 10. So this is going to be like height balanced binary search tree. One of the conversion of this linked list. You can easily see every node satisfies the condition of this binary search tree, and every node is also like height balanced. 0, this is the absolute value of L minus R. 1 is coming out to be 0, 1, and is also coming out to be 0. This is going to be like height balanced binary search tree. Now the concept or the main tricky point should lie over there, how we are going to build this binary search tree, that is height balanced binary search tree. So I'm just talking about two methods. You can build this height balanced binary search tree in two approaches, or I'm talking about this first one, and this first one should be like of time complexity O of n log n, and the second one should have the time complexity of about O of n. Okay, so I'm just talking about each and every one, and first one I will talk about O of n log n, and then I will come up to optimize this O of n log n to O of n. Okay, so let's talk about this O of n log n solution. Okay, so talking about the complexity of O of n log n solution, the approach is very going to be like very much simple. Find the middle node, and that is I'm starting from the beginning of this array. Like find the middle node and try to build up the left subtree and the right subtree. That is, I'm just following it up like top to bottom approach. Like I'm just first building this root node and then building this left subtree and then building this right subtree by considering the case like the heat, it should be heat balanced, like nodes in this left subtree and this right subtree should have the count difference of at most 1. Okay, so I'm just finding out the middle node, this 8. Okay, and if this is 8, so I will take this as the root node and I will try to build up the left subtree and right subtree. Now you can see I will call the this function recursive function. It should be recursive function for this left sub part, and then I will call for this right sub part. Now this 2 to 5 is another a linked list, and I will have to build a root node with left subtree and right subtree for this sub part also. That is, there will be another root node and there will be another root node which will be like left node of this node 8 and right node of this node 8 respectively. So this will be for 2 to 5 linked list with values 2 and 5, and this should be for linked list with values 9 and 10. Okay, that is, I am breaking my linked list into two subparts starting with the mid node. Okay, now in this case also, if you find out the middle node, it will come out to be 2 or 5. So again I'm just building it out 5, and again I'm just building it out 2. So it should be like here it will contain the value 5, and here it will contain the value 2, and here it will contain the value 9, and here it will contain the value 10. It is as simple as like that. So my algorithm for working upon would be like find out the middle node, then call for the recursive function for this left subtree, recurs for this left subtree, and recurs for this right subtree. If you focus on the method, it should be like this method is working exactly the same as like of merge sort. Okay, that is finding the middle point, then recurs for this left and recurs for this right. And if we have found the middle point, we can easily build the entire tree with the help of that. Note that this middle point has the value 8, a left value should have the value less than 8, and right has the value greater than 8. Okay, so this is also for following the condition for balanced search tree, or it should be like binary search tree. Yes, it should be like binary search tree. Now the condition lies how we are going to find out this middle node in this linked list. Since it is not a sorted array, if it is sorted array, I will just find out the middle point as starting index plus ending index divided by 2, as easily as that in a sorted array. But this is not going to be a sorted array. So how we are going to fetch the middle element efficiently? So we will use the two pointers technique, that is slow pointer and the fast pointer. Okay, so how this is going to work? This is going to be like key point for understanding this O of n log n solution, and this has been asked in many interviews. So you need to keep a brief idea how to work upon finding the middle point with the help of slow and fast pointers. Okay, so let's talk about how we are going to build up that. Like initially, both is initialized as the head, or since I'm working on this entire linked list, I will talk about this head. If I will talk about this segment 2 and 5 or any segment, I will talk about slow is starting with the start, that is slow and fast initialize with the start pointer of this linked list. Okay, and fast should be initialized with the head pointer. Okay, note that I am talking about this entire linked list now. So in any subsegment, you will talk about slow and fast exactly equal to the start point of this subsegment. Okay. Now at every step, I will increment my slow by 1, and but I will increment my fast by 2 moves further to the right of this linked list. And the reason behind this is simple. If I'll increment this fast by every time by 2, my fast will reach twice as faster as the times the by slow will reach. Okay, so if I will have this arrangement of this linked list, my slow would be at this position and fast would be at this position. Now at in next step, I will just increment my slow by 1 and fast by 2. It should become like my slow would come up to this one, but my fast would come up to this one. And what is my next step? My slow will come up to this one, but my fast come up to this one. But you can easily see my fast pointer will reach at the end of the linked list now. That is end of this my current subsegment. If I'm talking about a subsegment of this linked list, okay. So my fast pointer reaches the end of this subsegment. Okay. So you can easily see this slow pointer will talk about the middle node of this linked list. Okay, so I will use this concept of slow and fast pointer to find the middle node of this linked list for every subsegment I will be talking about. Since this is not an array, I will use this concept. If it is an array, I will directly fetch this with the help of indices. Okay, so this is going to be like the approach for this OFN login. So let's talk about this code now. I've already submitted this code. You can easily see. So okay, so this is what I think. This is for OFN, and I will talk about this OFN login. Okay, so you can easily see what I have done is since head equals null, I will return the null because you can easily see if you look at the constraints, that is number of nodes can be 0. Otherwise, I will return a call a function, recursive function convert to BST, passing this as head and another parameter as null. Okay, so I will pass this as head. First parameter is head. It should be like that is I am passing the start address of this current subsegment of this linked list, and the ending one should be like null. That is the end of the linked list. Okay, and you can see convert to BST takes two arguments, start and end, as okay, start and end. Okay, so if we start is going to coincide with this end, it means that we have already exhausted all the nodes that I should add upon to the tree. So I will return the null. Otherwise, I will take two pointers, fast and slow. Find the reason behind this. I will use this step. You can easily see this 6 line step is for just finding it out the middle node of this current subsegment of this linked list. Okay, so I will increment my fast 2 times and increment my slow only 1 time. So this will end up by giving me the middle node of the current subsegment being given by this slow pointer. This should be fast should is not equal to end, and fast next should also not be equal to this end. Okay, so then fast should be incremented 2 times and slow should be incremented by only 1 time. Now slow pointer contains the middle node. Then we will try to build a node for this current subtree. Okay, so it should contain the value of this middle node, and we will recurse for left and right subtree to build this node. And it should be like calling the convert to BST function, recursive function again with the start pointer as the start and end pointer should be initialized with slow. And nodes right should be like again slows next, that is for the remaining part after this middle node, slows next and up to this end, and finally we will return the node denoting that we have just done for this current subtree. And this recursive function will build up for this entire tree, that is the Bahit balanced binary search tree, also called AVL tree, from this sorted linked list. You can easily see runtime is called as runtime for this submission is 28 ms, and our runtime bits is like 71.21% of CPP submissions. Okay, this was for the OFN login solution. That let's talk about how to build up this height balanced binary search tree in OFN time complexity. Okay, so let's move. Okay, so let's talk about this OFN time complexity solution. Okay, so in this case, you can easily see if I will try to build a binary search tree, let's try to first understand this thing. So suppose this is a binary search tree. So it is obvious that the element or the value of this node, that is I am talking about this extreme left node of extreme left leaf node of this binary search tree. Okay, that is this node. So this node have the value exactly equal to the minimum value of all the nodes present in this binary search tree. And the reason behind this is quite simple. Every node has the value less than every node has the value greater than the value of this left child node but less than the value of this right child node, and this node is the extreme left of this binary search tree. It will contain the minimum value of all the nodes. Okay, now if this will contain the minimum value of all the nodes, if I will try to convert this linked list to a heat balanced binary search tree, and a start of this linked list is going to contain the minimum value of this entire linked list sorted in ascending order. So I must focus to fill this 2 over here. Okay, So the idea to build up this logic is very simple. This node will contain the minimum value, and what is the minimum value of this entire linked list? It is 2. So I should focus to fill this 2 over there. So how we are going to do that? It is again a recursive function. So but in this case, every node, that is every linked list node, is going to be accessed only one time, rather than in previous case, that is for current segment, what is the worst time complexity that we need to get for finding the middle element? It is like O of n. Okay, so but in this case we are just accessing every nodes only one time. So our time complexity is O of n. And how we are going to do that? Okay, so let's try to find it out. Okay, so suppose we have this current segment consisting of n nodes, that is this entire linked list. Now what I'm going to do is I'm just writing an algorithm for this O of n approach. If n is going to be like less than 0, return null. So I'm just explaining how why this is also always like return null, or I just also explain how I'm going to write that also. Okay. So otherwise, how many nodes that is going to lie in the left subtree? Okay. That is, if I will just partition my linked list into two halves, considering middle as the middle node and then left as n by 2 nodes, left will contain n by 2 nodes and right will contain n minus n by 2 minus 1. That is, if I have here n is equal to 5, then left node will contain, that is the left subtree will contain two nodes, and right subtree will contain 5 minus 2 minus 1. That is also this 2 node, and this one should be the root node. Okay, so in the previous case I will just found this root node, that is this root node or this middle node. Okay, this middle node, and then build up this left subtree and right subtree. In this case we will try to build up this tree, heat balanced binary search tree, from this root. Okay, so I will like from this bottom bottom to top, like from this leaf to root node. How I'm going to build up that? By starting with this minimum one. That is, I will call, that is for every subsegment, I will recurse for this left one first, rather than finding the mid node. I will recurse for this left one and passing the size of this segment n by 2. That is, if I am n equal to 5, I will recurse for this left subtree first, passing 5 by 2, that is coming out to be 2, and again I will recurse for this left subtree also. That is for this one. Again for this left subtree, I will call as parameter as left, I can call for the left subtree left comma 2 by 2 equals 1. So I will end up this one. If I will end up to this one, I will just form a new node whose value is going to be initialized with this 2. Okay, so new node whose value is initialized with this 2. Now I will call for a right subtree function at this step. How I am going to call? Then call for the recurse right, and passing the parameter argument as n minus n by 2 minus 1. That is the current step, number of nodes in the current step of this recursion to the right subtree. That is, it should be like n minus n by 2 minus 1. It is simple. Note that if I am just passing it out this parameter, note that this 2 has been initialized, new node with value 2. After doing that, I just need to increment my this pointer of this linked list. That is, after every step of assigning, you must be careful that my new node should be assigned as 5. So I will increment my reference pointer head to next. That is, it will assign 5 now. Okay, and you can easily see how I'm just building up this entire this tree, heat balanced binary search tree. You can easily see the entire building is should be like in order fashion. Okay, so let us try to understand this algorithm in more detail in the coding part also. I will explain a little bit in there also. Okay, so let's move further. So you can easily see this O of n time complexity solution has a runtime of 24 ms and it is faster than 91% of CPP summations. So the reason is or the solution is going to be like very much simple. First I have found the count of nodes in O of n time using this function. Okay, and then I will build the AVL tree. Note that I am passing this head pointer's address. Okay, So because I need to just increment my node of this linked list every time by one. Okay, so I need to just maintain a reference pointer of this head. Okay, so if n is going to be less than 0, I will return this null, denoting that I have just found that I'm just at the end of this building the tree. Okay, otherwise find this left node first. Note that this fashion is going to be like in order fashion. Okay, building this tree in order fashion. In the previous one, I have built this tree from this root node, then records for this left, and then records for this right. It should be like in the fashion of pre-order, I think. Root, left, and right. Okay, in this case, I am building this tree in order fashion. So I will build this tree for this left subtree, and this will go on up to that case till we have just builded, till we have utilized the very first node of this linked list. Okay, so you can easily see n by 2 I have just passed as the parameter argument. Okay, so make new node for the current subtree. If this recursion has happened for every left subtree, so I will just call this I will make this new node with the currents value, and then I have assigned this left node. Okay, then I will increment my next element in this linked list, because this is my 2, that is this element has been occurred, that is this 2. I will talk about this element now. Okay, so since the recursion is going to happen in order fashion, I must have to increment this. Then I will call for this right subtree, and in calling for this right subtree, what is my number of nodes in this right subtree? If we have n as the total number of nodes in current step of recursion, n minus n by 2 minus 1. Okay, then I will pass this roots right as assign this roots right as right node and return the root. This will give us the height balanced AVL tree. So if you have any doubts, do let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.